Dear colleagues, as we unfortunately had to cancel this year's World Congress in Montreal, we thought it would be a good idea to at least share some highlights from the virtual Congress that took place in February. Before the video starts, I would like to announce that the 2022 World Congress in Taipei, Taiwan will take place from June 9th to the 12th. I look forward to seeing you there in person, and now please enjoy the video. Oh, and don't forget to subscribe to our YouTube channel below for free so you can watch more videos in the next weeks. Thank you.
So welcome to this lecture on neurobiological research in ADHD and opportunities for personalized medicine. And I added a question mark in the end of this sentence because we're still very much in the beginning of exploring opportunities for personalized medicine. And I want to show you that today. Importantly, if we think about ADHD, we think about ADHD, or the clinical diagnosis of ADHD being the extreme of a continuum in the general population. So ADHD symptoms are normally distributed in the general population. And if you have many of these symptoms, this is when you are diagnosed with ADHD. The risk factors, genetic and environmental risk factors, are probably the same across the entire spectrum, across this entire continuum, and they are indicated here with arrows. They can have different effect sizes, and both genetic and environmental factors contribute here. So the continuum of ADHD in the general population. If we go back to the clinical phenotype and we ask the question, how does that look across the lifespan? Then we know that a number of the individuals that were diagnosed with ADHD as children will lose their clinical diagnosis as adults. And this is a study where Steve Ferrone and co-workers put together all the data from longitudinal studies and did a meta-analysis, and they found that at that time, the estimate of persistence from childhood into adulthood was about 15% of those diagnosed as children, but there was a very high percentage of people that kept impairing symptoms and functional impairment also as adults. By now, we think that this 15% estimate here is quite low. We think that at least half of individuals that were diagnosed as children will also go on to have ADHD as adults. And I want to show you a few studies from the Enigma ADHD working group. The first one being a mega-analysis of subcortical brain volumes and intracranial volumes in ADHD, for which we were able to bring together more than 1,700 cases and more than 1,500 controls from 26 cohorts across the world. And what Martine found was that almost all of the features that she investigated, so most of the subcortical brain volumes, the limbic system, the striatal system, but also the intracranial volume, so the total brain, a measure for total brain volume, were slightly smaller in people with ADHD compared to healthy individuals. And this is shown here as a Cohen's d and an effect size measure. An effect size measure of minus 0.19 for amygdala, for example, means that the amygdala of people with ADHD is slightly smaller than the amygdala of people that do not have ADHD across the board on average. So this doesn't mean that everybody has a smaller amygdala. So with this study, we were able to also, for the first time, really look at adults with the disorder. And what we found was that the differences that we see in the brain measures are actually found in children, but not so much in the adults that have the disorder. So what we concluded from this first study was that sample size was indeed an issue in imaging studies of ADHD. We find more if we put data together and the effect sizes of the findings are small. Total brain volume and most of the subcortical volumes are slightly smaller in people with ADHD on average, and effect sizes are attenuated in the adults, so the findings are more related to childhood ADHD. So as I said, effect sizes are very small in the brain features related to ADHD. The question is whether this might point to substructure in the data, meaning that only some of the people with ADHD actually have a certain smaller brain volume or brain feature. And we investigated that in part of the Enigma ADHD working group data, and we used boys in this case because it was the largest and most homogeneous part of our data set. And Ting Li, who just defended her thesis in my group, used the subcortical volumes as well as hippocampal measures to ask the question whether there is subgroups within our data. The first step that she did was a data reduction step, and here she found that exploratory factor analysis pointed her to three latent factors: the basal ganglia, the limbic system, and the thalamus. And using these latent factors from the exploratory factor analysis, she then performed a community detection analysis to find whether there are subgroups in our data. And she indeed finds such subgroups. She finds 4 communities. She finds the same communities in patients and controls. But if we look at the extremity of these communities, of the measures in these communities, then the case control effect sizes are larger within the communities than in the total sample. And this is what you see here. If we look at the total sample, we see small effect sizes. If we look at individual communities, we see larger effect sizes. For example, here for the basal ganglia, in community 1, there seems to be even larger basal ganglia than in the healthy population, whereas community 2 and community 3 are the communities where the measure is, the basal ganglia measures are smaller in people with ADHD. So there's a lot of heterogeneity indeed in these data. So we need to take this into account if we want to go towards personalized therapy in ADHD. Just to say that in the community 1 and community 4, we find more comorbidity than in community 2 and 3. So there seems to be some biological validity in these communities. And interestingly, community 3 is no longer present in healthy adult males, but it is still present in males with ADHD. So this suggests that that perhaps the brain of people with ADHD retains some features that are more related to childhood, to the childhood brain than other people. And this is in keeping with other findings of delayed brain maturation in people with ADHD. So summarizing, substructure exists in brain alterations in people with ADHD. We investigated this only in males, but I expect that this is only the case also the case in females. And we find that in brains of adults, adult males with ADHD, some features of childhood may still be present. So with that, I want to give you some take-home messages in the light of the theme of this session, opportunities for personalized medicine. Differences in brain structure and function do exist between people with and without ADHD. Differences in brain structure alone Also, gray matter structure alone are too small to support clinical decision-making. If we want to go in this direction, and I think it's promising to go in this direction, in which investments should be made towards the integration of data from different brain imaging modalities. Also, other types of data like genetics, the polygenic risk scores, may be important to include here, and it would be important to use advanced machine learning methods for that. And efforts towards the development of imaging biomarkers and personalized medicine for ADHD need to embrace the inter-individual variability in the brains of people with ADHD.